Now that we're starting to talk about electric circuits, another thing we can discuss when talking about circuits is power and energy, because that's the purpose of electricity, at least in our culture, to be able to supply energy long distance. So a power company, some maybe miles or hundreds of miles away, generates power through nuclear power, burning coal, oil, natural gas, geothermal, wind, solar, whatever. But that power has to get to you. And it gets to you via electric circuits, right? Large power lines that drive electricity great distances in order for it to get to your household. So unless you live, cabin in the North Woods without power at all, in which case it'd be almost impossible to watch this podcast or this lecture online without any electricity to power your laptop, to power the wireless network or a wired network that you're using, the lights to see when you're reading your book. These things supply power to your house, right? So you can use the power generated elsewhere. Well, let's talk about this power and energy in a circuit. Well, recall when we talked about electric potential, V, electric potential was defined as the potential energy over the charge on an object. So rearranging that equation to solve for potential energy, the potential energy, or electric potential energy, is equal to the charge on an object times the electric potential that that object is currently sitting at. So let's say an electron sitting at a potential of 10 volts. You can plug in the charge of an electron, plug in 10 volts, figure out what the potential energy is of that electron. Well, power, going back to last semester, the relationship between power and energy, power is just energy per unit time. How quickly is energy expended? Right, that's the idea of cars. So if you think of power in terms of watts, like a light bulb, 100 watt light bulb or a 40 watt light bulb, that tells you how many joules per second that light bulb gives off, the power of that light bulb. Well, power is energy over time. Well, the energy here, we talked about potential energy or electric potential energy over time. Electric potential energy is related to the charge and the electric potential. So I replace the potential energy with the charge and the electric potential over time. Well, if I rearrange this equation and group charge and time, the amount of charge that passes through some area in a unit of time is the current. We just talked about that a few lectures ago. So the power in an electric circuit is equal to the current in that circuit times the potential across that circuit. So it gives us an understanding of power in a power line. For example, high voltage lines, you might see warning 10,000 volts. Well, if you know the voltage is 10,000 volts, if you know how much current is flowing through that wire, you can determine how much power that wire is transporting. Voltage alone is not enough. If you know the resistance in the wire, you can find the current and then plug it in. And that's a good point. Since we know Ohm's law, V is equal to I times R. I think I had R times I in the last video, but this is typically how it's written in most textbooks. V is I times R. That's Ohm's law. I can replace this potential V with I times R. So I have I times R, which is I squared times R. So I can rearrange, take these two equations, algebraically put them together, and come up with an equation that gives the power is equal to the current squared times the resistance. Or I can solve Ohm's law for current, plug it in here, and I get the power in an electric circuit is equal to the potential squared over the resistance value. And this last one is usually the one that most people use when calculating the power in a circuit element, because the resistance value of an object is usually fixed. The potential across that object you can measure using a voltmeter very easily. So you can use this equation to figure out the power across the resistor. Now, a wonderful example of this, most of you probably have used a hairdryer or a microwave at some point in your lives. Hair dryers, if you purchase them, on the side it's written how many watts that hairdryer is. 1,200 watts, 1,800 watts. 1,000 watt hairdryer, 500 watt hairdryer. that wattage tells you how hot that hairdryer gets, right? How much power that hairdryer puts off in terms of temperature and wind speed. Well, if you know what the voltage is in your house, and most of you probably do, it's 110 volts typically, you can actually calculate what the resistance value is of your hairdryer. Likewise, a microwave. Microwaves are typically, 1,000-watt microwave, 1,200-watt microwave. You can go into convenience stores and they actually have more powerful microwaves, 1,700 watts. If you've ever read the instructions on microwaving a burrito and it gives times, sometimes it says, oh, for convenience store microwaves, you don't have to microwave it as long because they're more powerful. Again, if you know what the power is, you can figure out the voltage. If you know what the voltage is, across the microwave is being supplied with, you can figure out the resistance of that part of the circuit. So, power, you have three equations here depending on what material you know from the circuit. If you know the current and the voltage of the circuit, this is the version you use. If you know the current and the resistance of the circuit element you're looking at, it's the second version of the equation. And if you know the voltage and the resistance, which is usually the ones you know, it's the third version of this equation. They all give the same value for a circuit element. Now, your house uses power. If you've ever noticed, wandering outside, you have a power meter on your house, a little dial that spins that calculates how much electrical energy your house is using. And of course, the electric company comes by every once in a while and reads that meter and then determines how much power you've used since the last time the meter was read. And then they charge you for the power usage. Well, they don't charge you by the power. They don't really care how much power you're using. Really, they care about the amount of energy you're using, right? They don't care if you use a lot of power for a short time or a little power for a long time. Those two things might use the same amount of energy. So your power bill is really an energy bill, right? How much energy did you use? They don't care how fast you used it. They just want to know what the total amount is. So solving this equation, power is energy times time, I can solve it, energy is power times time. So energy, typically the SI units for energy is joules, but your electric company doesn't use those units because most people don't know what a joule is. If you've ever read your power bill, you'll see that the energy is typically given in a unit called a kilowatt hour. Really odd unit. Kilo meaning 1,000, right? Kilowatt means 1,000 watts times hours. So it's a combination of units. But if you think about it, it makes sense. If energy is power times time, power is measured in watts. That's the SI unit of power. Time is measured in seconds is the SI unit for time. But power can also be measured in kilowatts. Time can also be measured in hours, right? Those are other units of power and time. So a kilowatt hour is actually a unit of energy. Even though it has the word watt in it, it is not a power because it's being multiplied by time. And kilowatt hours are a little easier to understand for household use because if you think about it, a kilowatt hour is 1,000 watts for an hour. So if your hairdryer is 1,000 watts and you turn it on for an hour, that's 1 kilowatt hour of energy that you used. If you have 10 100-watt light bulbs in your house and you turn them all on for an hour, 100 watts for an hour is 100 watt hours, times 10 is 1,000 watt hours, which is a kilowatt hour. So it gives you an idea, given the power demand in watts of the objects that you're using, microwaves, dishwashers, washers and dryers, and so on. You can actually calculate energy in terms of kilowatt hours. And if you go read your power bill, you'll see that that is how they bill you. So many cents per kilowatt hour, which allows you to calculate roughly how much it costs to run a light bulb. Let's say you have a 100-watt light bulb, a yard light outside that you keep on all night, right? You live in a bad neighborhood and want to, make sure that no one messes with your door or your stuff. 100-watt light bulb, let's say you keep it on 10 hours, from dawn to dusk till dawn. That's 1,000 kilowatt hours. So look at what your bill is per kilowatt hour. Let's say it's 15 cents per kilowatt hour. that means it costs 15 cents every night you leave that light bulb on. So if you leave the light bulb on for 365 days, 15 cents times 365 gives you an idea of how much it would cost you to run that single light bulb for a year.